Yes, good morning.
So,
Good morning. Okay, so in the yesterday's class, we completed this. So your module 1 is complete. Okay, so it means 20% of the program syllabus is completed. Okay, so this is what we understood in the previous class: exceptions, interrupts, vector table, and core extensions. Okay, so your module 1 is done. Now we are about to start the module 2 now. Okay. So previous class, you people understood whenever there is an exception, whenever there is a runtime error, okay, or whenever there is an interrupt which is generated either by the user. So when I say user, will request the kernel to generate the signal. So I gave you the example of Control C, and the interrupts again they can be from the external devices. So whenever the interrupts are generated or the exceptions occur, so what happens is a PC will be set with the address of the interrupt vector table. And this interrupt vector table contains the uh, interrupt number and the corresponding interrupt service routine address. Now then the PC will be set with the address of the corresponding interrupt service routine, and then the function which is there inside the kernel gets executed. So these are a few things that we went through in the previous class, and then you also understood various examples, that is the reset interrupt, and then the undefined interrupt, undefined instruction interrupt or exception. So many things like this we understood, and then we started understanding the core extensions. So core is the central part of the ARM processor, which is mainly responsible for performing the execution of the instructions. And that is why we call it as an execution engine. Core is the execution engine, and this core is surrounded with many additional components which are called as extensions. And what the components are called as assistants. What they are going to do, they're going to assist this main core in performing the tasks at a much faster rate. And we looked into the advantages of adding, say, it improves the performance, okay, and then many other things. And then we looked into the three important extensions. One is the cache and TCM, tightly coupled memories. And the other form of extension is the memory management. And the third one is coprocessor. Hope you people remember all these things. These things were covered in the yesterday's class. Do you people remember these things?
Yes, sir.
Okay. And then this cache and TMC we understood. So that means we have something called as tightly coupled, sorry, this unified cache and split cache. So within the unified cache memory, we have both data and instruction present. Now in this sits in between your core, ARM core, and the main memory. So because the performance of the main memory is not comparable with the performance of the cores, so now we need a much faster memory which can almost operate at the speed of the ARM core. Now for that purpose, we have the cache memory sitting. And again, in this cache memory, two types you can have. One is unified cache memory and split cache memory. When I say unified cache memory, both the data and instructions are held inside it. And there is a common data path again, common data and instruction path. So the disadvantage with the unified cache memory is that it is not possible for you to simultaneously fetch instruction and data. So you got to do it one by one. First you have to fetch the instruction, and later you should go for fetching the data. And then with the split memory, it is possible for you to simultaneously fetch the both data and instruction, because it has separate memory, separate cache memory for data and separate cache memory for instruction, and the separate paths also, separate data path and separate instruction path. And then we looked into the memory management, why memory management is necessary. So it is the main controlling unit for all the memory devices, and also offer some kind of the protection when the process is executing and it wants to access the memory region of another process, so it will not allow. And three levels we understood: one with no protection, okay, and the other one is MPU, memory protection unit, with limited protection facilities, and the third one that we understood was MMU, main memory management unit, is full protection. And the last part that we understood was the core processors, sorry, co-processors. So again, these are the special process which adds to the main processor. I gave you one or two examples. So like IO processor, input output processor. Now the main core processor will not be involved in performing the IO operations. All IO operations, input output operations, will be taken care by the special core processors called as IO core processors, and the main core can involve in performing the execution of what? So some other program. So just speed ups. And similarly, we have the graphics core processors, something like this, etc. So now we are in the module 2, introduction to the ARM instruction set. So now here you'll start learning all the instructions. Okay. So though we have already started with few sample programs and the lab programs, so the actual discussion on the ARM instruction set starts from now. Okay. Now let me go here, the chapter 3, which is the module 2. Okay, so introduction to the ARM instruction set. So these are the instructions. So don't get panicked by looking into this instruction set. Sir, do we need to remember all these things now itself? No, not necessary. As and when we go, proceed, so you'll get to know these instructions. So at this point of time, no, don't worry. Okay, just have a look into this. So I have add C here, adds two 32-bit binary values and a carry. So because add with carry, it is something like that. And add, this is what we have already used, adds two 32-bit values, and which is a logical bitwise logical operator. Okay, so performs the ending of two 32-bit values, and B also you used. So back we used to write. So B is a branch instruction, and then there is something called as BIC. So a logical, it's something called as bit clear. Okay, bit clear, logical bit clear. Okay, so we'll understand why all these things are BLX. Okay, so as in we when we proceed, so you understand all these things. So let us not focus more on these things right now. So because few instructions you already know, so and compare also, in the previous class when I was explaining one lab program, CMP also explained you. Okay, and CLZ is there, so count leading zeros and many things. Okay, and MVN also you understood, MVN. So what is MVN? So don't look here. What is MVN? I gave you a sample program. Yes. What it gives? I've given one sample program. If you're written, you can turn the pages and see. What is MVN? Oh God. What is MVN? Hello? Please unmute and speak.
Negative value.
One's complement. It finds one's complement. Okay. So just a second. Okay, sorry. The MVN finds the ones complement and moves into the another register. Okay, for MVN, you can take three operands. One is the operand, source operand, which is holding the what? A number, and what it's going to do, it finds the ones complement of it and then moves it into the other register. So we have done a sample program on that. So please glance everything. Okay. So don't say, so only few instructions which were covered, but still you were not able to remember those things. And so multiply also we have used, and I don't know whether you people remember this or not. MSR, MSR. You remember this? I explained this. Any idea where we understood this MSR? Why we use? Yes. So it was explained. So if your status is something like this, no, very bad. So it is used to change the interrupt flags. So this is where I explained MSR. So I'm enabling the slow interrupts here. See, I've finished module 1. If your response is like this, then what is the use? I don't know. I guess I've spent nearly 3 to 4 minutes on this slide explaining. See, if people are not able to recall what I've done yesterday, I guess this was done yesterday, not a week ago. And please don't be under the impression that, so now also it is online classes, and so you will not be having the exams. It cannot be done so. So it is almost 2 years, and 2 years half of the degree will go without. They cannot do like that. They'll postpone and they'll conduct the exam. So when I'm putting 100% effort, at least 80% effort should be there from your end. It is only few instructions which I've told in the previous classes, earlier classes, and you're not able to remember them or recall them. When I ask something, I don't want the 100% correct answer. At least some attempt you should make, 50 to 60%. So, okay, let me see from the next class whether the same status continues or not. Okay. Okay. So I was just trying to highlight or show you a few of the instructions which we have already used or come across. Okay. We have used some instructions in the program and some instructions, as I mentioned, MSR. So we have discussed them as a part of the lecture slide. Okay, but we haven't used them in the programs. And we are going to use all the instructions when we're writing the programs. So some we make use and some we don't make use. Okay, so this is a complete. These two slides are giving you the complete overview on all the instructions. Okay, ARM instruction set along with a line of description for each. Okay, so what we are going to discuss in detail each of these instructions along with the examples and how these instructions are going to operate and what are the functionalities that they are going to perform, what are the operands then operands they take, which one are the source operands and which one is the destination operand. Everything we'll be discussing in a short while. Okay, and this also I mentioned. Let me see whether you people tell it or not. SWI. So here it's already written. It's a software interrupt. Even this also we discussed. So whenever when are you going to use this SWI? This also I've told. So whenever from your program you need to invoke the execution of any of the routine which is there inside the kernel, it is by using SWI, software interrupt. SWI, and you got to just pass the function number. Say I want the execution of the function number 1 which is there inside the kernel, SWI1. The function number 1 is there inside the kernel gets executed. SWI type 2. Now what you're doing, you're interrupting the processor and telling stop executing my program, go to the kernel, perform the execution of the service routine 2 which is there inside the kernel. So it's something like that. Okay. So and STR also we have understood. So few of them which we have already used, those things I'm highlighting. Okay, STR and LDR also here. I don't know, it was somewhere here. LDR. So we have used. These are few instructions which we have used. Okay. So now, so we'll focus on the data processing instructions. So instructions which are used for data processing or data manipulation. Okay. So now again, all the data processing instructions which are available within the ARM7 design. So they work only when the data is available within the registers. For you to do any kind of data processing, the data must be brought to the registers. So if I say I have the data inside the memory, can't I do the data processing operation directly inside the memory? It is not possible. So you got to bring it to the registers. So that is the reason we call the ARM7 design comes under the category load and store architecture. Okay, so now what are the data processing instruction? Move is also a data transfer instruction because we have already discussed the move instruction. Move is one such data processing instruction. Why we call move as a data processing instruction? Because it helps us to move the data from one register to the another register. And then arithmetic instructions. Okay, so we have already used few of the arithmetic instructions like addition, subtraction, multiplication, all these things. Logical instructions and or not. So these are again data manipulation or data processing instruction. Comparison instructions. So we have come across one comparison instruction, CMP, and the conditional statement. So the conditional statements will not come here, the comparison instruction, and then the multiply instruction. Okay, and we don't have divide instructions here. Please do remember that. Okay, please do remember we don't have divide instruction in the ARM7 processor design. Okay, so these are some of and how the division operation is implemented. It's implemented using some other logic. Okay, so or a technique. So we'll know that later when we go to the further slides. You'll understand that. So not necessarily in this class, maybe after 1 or 2 classes you'll understand how division is implemented within the ARM7. But we don't have an explicit instruction with the name div available inside the ARM processor. Okay, so these are some of the data processing instruction. Any doubts here? Any doubts?
No,
So
sir.
at least for this you can say yes or no. Or you don't want to open your mouth permanently? You don't want to discuss with me? Any doubts?
No, sir.
No, sir.
Okay. The most data processing instruction, all these things. So they can process one of their operands using the barrel shifter. Even this also you're already aware. So one of the ALU input in ARM7 design processor is connected with the barrel shifter. Now using that barrel shifter and all this data processing instruction, it is possible for you to perform the shifting operation before you perform the actual operation. Okay, so I want to perform the addition, and before performing the addition I got to do some shifting operation on one of the operand, so then you can do it. So barrel shifter is used here to perform the complex instruction, execution of the complex instruction in a much simpler way. And what barrel shifter is doing here, it is basically doing the shifting operation, either the left shift operation or the right shift operation. And this comes to the logical. So whenever I say shifting, left shifting, logical left shifting, or right shifting, it is a logical operation. And I've already clearly told you that logical operations are the much faster operations than compared to any other type of operation. So you take a logical operation, so whether it may be and or not or left shifting or right shifting, okay? So try to compare these operations with the arithmetic operations or the comparison operations or the branch instructions. So these are the one which are much faster instructions. Okay, now, much faster in the sense they execute just within a clock cycle and even sometimes lesser than the clock cycle. Okay, next, and this also you're aware, we make use of the suffix yes on the data processing instruction when we want the conditional flags to be updated inside CPSR. So in case if I want to make my instruction, say I'm writing add instruction, I want to make my addition instruction update the conditional flags based on the result that is produced by the addition instruction. If I want to update the conditional flags, so then I can go for using suffix x. The moment I add the suffix s to the addition instruction or any data manipulation or data processing instruction, so they go for updating the conditional flags inside the CPSR. Hope you understood.
Yes, sir. Yes,
So
sir.
if you don't want your instruction to update the conditional flags which are there inside the CPSR, then you avoid using or skip using the suffix yes. Okay, if it is necessary, for it depends on what kind of program you're writing or what kind of a logic you're following. Okay, so if the situation demands you to update the conditional flags which are there inside the CPSR, then simply go for adding the suffix s to any of the instruction, or to majority of the data processing instructions you can go for adding the suffix s and you have the conditional flags updated. Next, so move and logical operations update their carry flag, negative flag. These are all the flags which we have already discussed. So carry flag, so negative flag and zero flag. So what is the other one?
Overflow flag.
Overflow,
Overflow.
overflow. And there is one more as well, saturation flag, and that is we are not going to use it. But these four you got to remember: carry flag, negative flag, zero flag, and one more is overflow flag. So if you take move and logical operations, move and logical operations, by default they're going to update the carry flag, negative flag, and zero flag. Okay, so carry flag is set from the result of the barrel shift as the last bit shifted out. Okay, so one of the example I can think I'm not shown to A section. I guess I've shown it to the section C. Okay, so whenever you're performing some operation, if there is a carry generated, then the carry flag is set. Okay, even when you're shifting, okay, the left shift or the right shift during the barrel shifter, if the last bit gets shifted out of the register, then also the at that last shift, last bit which is getting shifted out of the barrel shifter, so comes and sits inside the carry flag. So next further slides, so there are few things how the shifting happens within the barrel shifter. There you'll clearly understand this. So next. And the negative flag, the as I already mentioned, the most significant bit, the 31st bit, okay, is the one says whether it is a positive number or a negative number. If the 31st bit is 0, then it is a positive number. If it is 1, then it is a negative number. And then 0 flag is set if the result is 0. Whenever ALU, the most recent operation that is performed by the ALU is resulted in a 0 or result, then the 0 flag will be set. Now time to understand. So after all these things, okay, so the first instruction, move instruction, with which you are already familiar, okay, so it is the simplest ARM instruction because it just moves the content from one register to the another register. So not necessarily the content from one register to the another register, it also moves an immediate number to the register. Okay, so this is what is written here. Moves or copies also, you can say it copies n into the destination register RD, where n is a register or an immediate number. So why it is not written as something like Rn or Rm? So because so the source to the move instruction need not be a register all the time. It can also be an immediate number. So that is the reason we have taken the notation as n here. And this n, it can be a register or it can be an immediate value. And why this move instruction is useful? So this is useful for setting the initial value. Okay, say for example, in the previous programs, so we did the factorial program, okay, and we did the addition of first 10 integer numbers. Do you people, can you people recall those two programs which we did? Addition of the first 10 integers. What we did, we took a register, okay, the sum. So in C programming language, we used to write it as sum is equal to int sum is equal to 0. And the same way here in that program, in that assembly program, when we wrote, what we did, we took some register and we moved the value 0. Now what is that? So in that register, I'm taking the initial value as 0. That is the initial sum as 0. So normally move instruction is used for setting the initial values inside the registers. Okay. Okay. And so it is also used for transferring the data between the registers. Now the syntax, it goes something like this. So instruction. So it can be what? MOV. So the mnemonic name is MOV. MOV. And it can be followed by, see, the one which are written inside the curly bracket are optional. Okay, the one which are written inside the curly brackets are optional. Let me take a pen and write. So instruction is move. Okay, and move n also we have understood. This instruction can be either this move or MVN. Just understand the notation here. So move, and the one which is written inside the curly bracket is optional. That means it is not necessary that you got to embed a condition inside the instruction. So in the previous classes I was mentioning, conditional execution of every instruction is possible. That means you can embed the condition inside the instruction itself. So in case if you want to do that, so then you can embed this. Hope people remember that these things which I mentioned in the earlier classes. So when I was explaining this conditional instruction execution, I came to this slide and I showed you this is what I showed you people. I don't know whether you people remember it or not. Do you remember?
Yes, sir.
Yeah. So move, and this condition is optional. That means it is not necessary all the time. And yes suffix, the one which I mentioned here, the suffix yes is also optional. And RD and N, they are not optional, they are mandatory. Okay, so remember the one which are written inside the curly bracket are optional. So these two are optional, and this is mandatory, and this is destination register, and this N can be either a register or an immediate number. Okay, so now move condition. If there is a condition, you specify it, and if you want the conditional flags inside the CPSR register to be updated, use the suffix yes, and then specify your destination register and specify your source. And this source n can be either a register or an immediate number. Okay. Now what move is doing? Move a 32-bit value into the register. So that is nothing but you're assigning the immediate number or the content of some other register to RD, destination register. And similarly, the other is MVN. Okay, move negation, something like that. Now what it will do, it will move the not of 32-bit value into a register. So now how do you represent the negation? So negation is something like this. And again, so we are writing it here. That means this n can be either an immediate number or a register. So what this is going to do, MVN, it will negate this and then it will assign it to the destination register. Hope you understood.
Yes.
Yes, sir.
Okay. So when you're if you're asked to explain the move instruction, this is how you got to write it. Okay, the syntax: instruction, condition, optional suffix yes, so destination register, and then the source, and then move and move and what they do. Okay, next. I have the example here. Say this is before. Okay. I am assuming I have the value 5 in R5 register and value 8 in register at 7. Now I'm saying move at 7 comma R5. Now what is that I'm trying to do? I'm trying to copy the value which is available in register R5 to R7. Now after this move instruction is executed, so the post condition is something like this. So this 8 which was 8, the value 8 which was there in the register R7, it is overwritten by the value 5 from the register R5. Okay, so this is what move instruction is doing. So you have already done it and you are completely aware of this. Okay, next. Condition embedded in IND instruction. Sorry, I made a mistake here. So this is not IND instruction. Can be condition embedded in move instruction. Okay. So now here you can see here. So I said this is condition, right? So move is the mnemonic, and this can be followed by an optional condition. Okay, and again yes is optional. Yes, I'm not writing. I've written the condition EQ. Move on equal the content of register R1 to R0. What is the meaning? This condition EQ, what I'm writing, before moving the content of register R1 to R0, it will go and check the zero flag. If zero flag is 1, is set means what? 1. What is the meaning of reset? 0. That you know, right? Set means
Yes,
what?
sir.
1. If zero flag is set, okay, then only it will move the content of register R1 to R0. So if I assume the zero flag is not set, so zero flag value is 0, then we don't have the value which is available in R0 moved to the register R1. That means this instruction is conditional execution instruction right now. It gets executed only if the condition is true. What condition? If the zero flag is set to 1. If the zero flag is 0, we don't have this instruction getting executed. It's clear? Clear?
Yes, sir.
Okay.
Yes, sir.
Now I have an example on this. Okay. Now have a look into this. Move. So this is immediate number now. I'm moving it to the register R0. I'm taking another immediate number 6. I'm moving it to the register R1. Now what I'm doing, sub s, you can see here, subtract. Suffix s I'm using because I want the conditional flags to be updated. And I'm not using any condition here. There is no condition embedded. Now what is that I'm trying to do? From R0, I'm trying to subtract 4. R0 is 5. I'm moving 5. 5 minus 4 it is. So the result will be what? 1. Okay. Result is 1. Now, is the zero flag affected? No, because zero flag gets set to 1 only if the result of this operation is what? 0. Right now the result is 1. 5 minus 4 is 1 you're getting. Next, what I'm doing? Move EQ. So to the move instruction, I'm embedding the condition EQ. R2, comma R1. Move the content of register R1 to R2 only if what? Only if
Zero flag is
Zero flag.
Zero flag is 1. Okay. Only if, let me write, only if z is equal to 1. But what this is doing now, 5 minus 4, what we got, the result is 1, which is a non-zero value, okay. Now the zero flag is not set, zero flag is still 0. Now this statement will not get executed, it skips this. That means you will not see the content of register R1, that is 6, will not be moved to the register R2. And next, what we are doing, we are moving the immediate number 10 to the register R3. Okay, so just one more instruction, I'm just moving, and then back be back, and then end. Okay, so let us now quickly execute this and see how this statement, is skipped from execution. Okay, it will be skipped. So as per as this status, this 5 and 6 status, so this has to be skipped. Next, what we will do, we'll change this R0 value to 4. 4 minus 4, how much it is? The result is 0. Then you have the 0 flag set. Then what? The content of register R1 gets moved to the register R2. So we'll quickly execute this and see now. So like this, you get so many examples. Now I don't go for writing this, okay, manually as I did for the lab programs. So let me do copy paste, because writing again it takes time. Okay, so I'll close this project. So new project. Okay. So let me create a new folder here. Let me give sample 2. Sample 2. Okay. I'll copy now this. Okay, I'm saving this now. Sample 2.s. Okay, done. So we have saved a lot of time. Okay, let me add this to the source group 1 now. So the program is already explained to you. We'll debug it. Okay, add it, translating it, building it, now debugging. Okay, up to now. Let me. So if 11 I'm pressing, so 5 gets moved to the register R0. Okay, so 5 is moved to the register R0. Now 6 I'm moving it to the register R1. Okay, now I'm using, let me expand this CPSR. I'm using sub S. R0 is 5 minus 4 I'm trying to do. R0 gets the value 1 right now. Okay, R0 value will become 1, which is a non-zero value. You don't have the zero flag set. So zero flag will not be set. Okay, so just observe. See, zero flag is not set. It's still 0. Now move EQ. This is the condition embedded. So move, if zero flag is set, move the content of register R1 to R2. What is there in R1? 6. Just observe R2 now. It will not get the value 6. So because zero flag is not set. See, observe R2. That means this instruction is not executed. So execution of this instruction is skipped. Okay, because the condition was false. Now I'm moving the immediate number 10 to register R3. R3 will get the value A. Got the value A and then back B back. So now what we will do, we'll do one more run. I'm stopping the debugger. Now I'll change this to 4. R0 value intentionally I've made it as 4. Now again, after doing the changes to the source, don't forget to translate it for one more time, build it for one more time, and then debug. Okay, so I'm moving 4 to the register R0, 6 to the register R1. Now I'm subtracting 4 minus 4, the result is 0. Now the CPSR should be updated. So I'm pressing F11 now. Okay, see, 0 flag is set now. 0 flag is 1. Now I have the condition embedded here. Move on equal the content of register R1 to R2. What this equality EQ condition will do is it will examine the 0 flag. Now 0 flag is set. So now it moves the content of register R1 to R2. Now R2 should get the value 6. So R2 got the value 6. Now this case, now the execution of this statement is not skipped, it is executed because the condition was true. And after that I'm moving the value 10 to the register R3. Hope you understood.
Yes, sir.
Yes, sir.
Okay, so let me call the attendance. So I was not doing it all these days. Let me do it from today at least. So, and this is also important. So when I call, please answer your call. So I'm calling in my register order. Darshan.
Yes, sir.
Okay. Vidisha.
Yes, sir.
Adar Kumar Mishra.
Present, sir.
Abhishek Anand. Abhishek Anand. Okay, absent. Abhishek K.
Yes, sir.
Abin K. Ranjan.
Yes, sir.
Aditya DS.
Present, sir.
Aditya Gautam. Aditya Gautam. Oh, 1 second. Let me stop recording.